Professor, can I start now?
Yes, sure.
Okay. Yeah. So, good evening, everyone. Welcome to another session of the Network Seminar Series hosted by the Center for Networked Intelligence at the ECE and RBCCPS IISc. It's my pleasure to introduce today's speaker, Professor Washim Uddin Mondal. He will be speaking on sample efficient constrained reinforcement learning with generalized parameterized policies. Professor Washim is an assistant professor in the Department of Electrical Engineering at IIT Kanpur. He was a postdoctoral researcher from April 2021 to December 2023 at Purdue University, USA. He obtained both his PhD and BTech MTech dual degree from IIT Kharagpur. For a brief period in 2016, he worked as a quantitative financial analyst in WorldQuant, Mumbai. During PhD, he conferred with the Prime Minister's Research Fellowship, and his thesis was selected as one of the national winners of the Graduate Thesis Evaluation in 7-minute competition organized by IEEE Communications Society. He has both co-authored multiple papers and has served as a reviewer/TPC member in various reputed venues such as IEEE Transactions, IEEE ICC, AAAI, NeurIPS, AISTATS, etc. He has also worked as a consultant to the Indian Army to solve problems of national interest. We request the audience to keep your microphones on silent for the duration of the talk, except when asking questions. And for questions, feel free to unmute yourself and ask directly or type them in the chat box and we will relay your questions. Over to you, Professor.
Thank you for the kind introduction. So I hope I'm audible.
Yes, Professor.
Okay, thank you. So the title of today's presentation is Sample Efficient Constant Reinforcement Learning with General Parameterization. So before going into the details about this talk, I would like to introduce you some motivational example. So the AI and the ML algorithms that are coming out nowadays that you can see. So the basic motivation is to try to learn the way humans have been learning through ages, not through hard-coded instruction, but from intuition or finding patterns in the data. So in this slide, I have given two examples of learning paradigms. So in the first case, you can see that some of the children are they're trying to identify several human parts by looking at the model humans made out of some plastic. So this kind of a learning, when you learn from examples, so they are specifically called supervised learning, and there are several examples, several ML algorithms are available which follow this kind of learning paradigm. So the other kind of learnings, which can be stated as the learning by iteration, and this is kind of relevant to our talk. So in this learning, what we do is that you try out different strategies at first, and you observe the effect of these different strategies, and then from those observation, you try to modify your strategies, and eventually you learn how to navigate through an unknown environment. So, for example, let's take the example of the learning when you try to learn to drive a car. So in this case, so in the first try, you might not be able to drive it very properly, but after a couple of tries and trial and error, you will be eventually able to find out how to navigate through the roads. And similar is the case for when you try to learn to cook a delicious meal. So in the first few tries, you might not be able to come up with a very good recipe but after a couple of tries, you might be able to do so. So if you closely look at this type of learning, you can see that there are two main components present in this type of learning structure or this kind of learning hierarchy. So in the first component is typically called the environment, which is kind of a dynamic environment, which is typically characterized by a time-dependent state. And then is another component, which is called the agent or the policy approximator, or it also is called the learner, which is trying to learn to navigate through this environment. Now, the agent takes different actions at different time instances, and as a result of this action, the state of the environment changes to a different state, and also feedback is generated in the form of a reward signal. So if you take the example of the car driving scenario, so in this case, the states could be the traffic road condition that the driver can see through the window of the car. And also the actions could be the actions could be categorized as whether to accelerate the car, or whether decelerate the speed, or whether to steer the car in the left and the right direction. This could be categorized as different types of actions. And if the learner is trying to reach a certain destination within the shortest amount of time, then the reward signal could be the amount of distance that the car is covering per unit time. So in this type of examples, the main target is to come up with a certain kind of strategy that maximizes the sum of the rewards. And the sum is, most of these cases is taken to be discounted sum. So it has some physical interpretation, but mostly this discount is taken for mathematical convenience. And this kind of maximization has to be performed without any knowledge about the environment that you're trying to navigate. But in many of the practical examples that we also see that the agents not only have to maximize the reward, but it has to do so by abiding some rules. So for example, if you take the car traffic scenario again, then you can say that the agents are kind of trying to reach the destination within the shortest amount of time, but they cannot break any traffic rules while doing so. And if you break any rules, traffic, for example, if you are overtaking a car where it is not allowed, or you are hitting some pedestrian, then you might attract some small fines depending on what kind of damages you have incurred. To you can also get some severe penalty if the damage is too large. And let's take another example. So if you're familiar with the wireless communication, then you might have also heard about the cognitive radio network. So this is kind of a networking scenario where we have two different type of users. One of them is called the primary user, which are allowed to transmit whenever the need arises, and they are kind of legally entitled to do so. But there are other type of users which are called secondary user, which are not allowed to transmit when the primary is present. So where they can transmit whenever the primary is absent, or when there is a white space present in the network. Now, sometimes detecting the white space, that might be not as perfect. So sometimes the secondary user, they end up transmitting in parallel to the primary user, and that kind of hurts the transmission of the primary. So in these cases, the secondary's goal should be to transmit as many data as possible, but they should also keep in mind that their transmitter should not harm the transmission of the primary by a large amount. So you can see from these examples that we can also so apart from the reinforcement learning problem that I've described before, there are other type of or other classes of problem where the goal is to maximize the reward, but also abiding, but the reward, but agent also has to be aware that they should not violate any type of rules that has been preset by the environment. So these type of problems are categorized as constant reinforcement learning. So here the violation from the predefined rules that is indicated by a cost function. So here the goal is to maximize the sum of rewards while ensuring that the sum of the cost is within the certain limit, and the limit is this limit is predefined. Now, with this motivation, I would like to now introduce the formal definition of the constant multiplication process. So similar to the unconstant setup, we also have a state space, which is indicated by the calligraphic X. So in this example, the S could be either finite or a countably infinite state. And we also have the action space A, so which is the collection of all the actions that the learner can take. And it can, so in this example or in this talk, I'll be assuming the actions to be finite with cardinality A. And we also have some transition function P, so which indicates that given the current state and the action, with what probability the next state will be achieved. And this transition probability is typically assumed to be unknown to the learner. And this is the typical characteristics of the RL problem. And so if the transition probability is known, so these type of problems, then solving the CMDP becomes a planning problem, not an RL problem. So in addition to the transition function, we also have the reward function and the cost function, and both of these functions are functioned from state and action space to some subset of the real number. And we also have some notion of the initial state distribution that is denoted by the symbol rho. And we also introduce the discount factor gamma. So it is used in order to compute the expected sum of rewards over a long horizon. And the discount factor is typically taken to be a number between 0 and 1. Now, these are the different components of the constant multiplication process or CMDP, and the objective of the learner is to come up with a strategy, some kind of a strategy to navigate this constant multiplication process in order to achieve some objective. So to quantify this concept, so we also introduced the concept of a stochastic policy pi, and the pi is kind of a mapping from the state space to the simplex over the action space, probability simplex over the action space. So it is essentially is kind of a is kind of a recipe that states that dictates to the learner that which kind of action should be taken at a certain state S with what probability. Now, with these definitions, we can now introduce the concept of a pi-induced or some policy-induced sample trajectory. So this is, so let's say you are starting from some initial state S0, which is drawn from the initial distribution rho, and you are keep on applying the policy pi repeatedly. So if you are at state S0, then from policy pi, you'll be taking an action A0, which will result the change of the state to S1. And S1, you can, again, you can, draw another action A1 according to the policy pi, and that will change the state to S2. So in this way, you can see that you can get an infinite sequence of S and A, and this infinite sequence of S and A that is evolved by applying the policy pi repeatedly. So that is called the pi-induced sample trajectory. So these definitions help us to concretize the notion of the objective function. So let's since we have two different type of function, both the reward and the cost function. So here we are defining this objective function in terms of an arbitrary utility function G. So G can take both the values of R and C. So we have a unified definition of the value function. So the Q function, this is very standard definition. So the Q function corresponding to any utility G, that is defined as the expected or discounted cumulative sum of utility values GESTAT that you observed over a pi-induced trajectory when the trajectory starts from a given state and action S and A. And in a similar fashion, you can also define the V5 function. So the state value function of the V5 function. So this is again an expected discounted sum of the utilities. These utilities are computed over a pi-induced trajectory, and the trajectory starts from a given state S. So here we do not initialize the action A. So if you take an expectation over this V function over all state S, and the S is drawn from the initial distribution rho, then we come across a function which we call the average value function. And this is denoted by the symbol J pi, G. Now with this definition, now we can define what is the central goal of the CMDP problem. So in the CMDP problem, we want to maximize this J pi R function, which is the average value function corresponding to the reward functions, but subject to the constraint that the average value function corresponding to the cost function that satisfies certain kind of constraint. So in this case, we have given the constraint as less than equal to 0, but it could be any other. We can also incorporate any other type of constraint as well. So we can do that by changing the reward function and the cost function by scaling and translating. And here the pi is, the optimization variable pi, the policy that is taken from the collection of all possible stochastic policies. So here you can see that why the cost was chosen, the range of the cost was chosen as -1 to 1 instead of 0 and 1 that was taken for the reward function. So if you take the range of the cost function as 0, 1, then you can see that the constant that you get here, that becomes kind of a trivial constant. So, and this constant optimization problem does not make much of a sense. Now, the question is, how do I solve this kind of constant optimization problem? So if you look at the function J pi G for both G belongs to, for both R and C, G value belonging to R and C, then you can see that this objective function is kind of a non-convex function of the policy pi. So the two kind of tool we have that may not be, it might appear that we might not be able to apply that, what the tools that we have for the convex optimization. However, interestingly, if you look at this function closely, then you can see that this J pi G function that can be written as a product of the G function and another function mu pi. So this mu pi function is defined to be the state action occupancy measure. So the mu pi is defined in such a way that V nu pi kind of becomes the probability distribution. And it is its intuition behind this definition is that this is kind of computing the number of times the CMDP is visiting a certain state action pair S and A, starting from an initial distribution rho. So you can see that from this kind of a decomposition that although the J pi G function, this is like a non-convex function of the policy pi, but it can be written as a linear function in terms of the state action occupancy measure. So, and also, if you look the relation between the policy pi function and the state action occupancy measure nu pi, then you can see that there is a bijection between them. So if you define the policy pi function, then the state action occupancy measure nu pi that also automatically becomes fixed. And if you fix the state action occupancy measure nu pi, then you can also recover uniquely the policy pi function. So there is a like one-to-one connection between the pi and the occupancy measure. So with these results, we can now write our central optimization problem that we defined for the CMDP as a linear optimization problem or linear programming type of problem. So our objective function now that becomes a dot product between the reward vector and the new vector. So new is kind of the state action occupancy measure, and now our constraint, the JFIC, that can be now written as a product between the cost vector and the new vector. Now, additionally, the new vector that also has to satisfy certain kind of stationarity conditions. So that is written as new equals to P new. So this is ensuring that new is a state action occupancy measure corresponding to the transition probability P. Now, this entire formulation, if you look at that, then it becomes clear that this is kind of a linear programming formulation. So, and linear function is a convex function. So there is a possibility then we have this possibility of strong duality for this kind of formulation. So the second statement, this exactly states that. So if we ensure that the Slater's condition, so which essentially says that we have some the non-trivial feasible solution pi bar, or some interior solution, interior feasible solution pi bar that is present, which is called the Slater's condition. Then the primal problem that we formulated earlier, that is the constant optimization problem, and the dual problem that we can formulate associated with that or primal problem. So these two problems will give rise to the same kind of a solution. Now, the dual problem that can be formulated by taking the objective function and some plug, and we have to add some Lagrange multiplier multiplied by the constant. So if you do that, then you can see that the optimization problem, min-max optimization problem that I've written here, so that becomes the dual optimization problem. So due to the strong duality, if you solve this dual optimization problem, that gives you the exact solution to the primal problem that I formulated earlier. Now, this kind of structure has been exploited, can be exploited, and this kind of structure is useful if the state space is small and finite. And in this case, the new vector that can be written in the tabular format, where the size of the table is S cross A. And in fact, there are many papers that have shown that exploiting this kind of linear programming structure, it is possible to come up with a algorithm that identifies a policy that is epsilon distance from the optimal policy, and that satisfies the constraints given by the CMDP. And this algorithm achieves this optimality, epsilon optimality, with a sample complexity that grows as 1 over epsilon squared. However, if the state space is very large or if it is infinite, then this kind of the solutions or this kind of algorithm that no longer works. Now, what other type of the avenues we can explore in order to handle this large state space? That becomes the next question. So there is another approach which is called the linear CMDP. So in this approach, what we assume is that the Q function and the V function that we defined earlier, that can be written as linear function of some known low dimensional feature vector. But this is kind of a not very realistic assumption, so it has limited applications. Now, what I'll be talking about in this talk is related to what you call the general parameterization. So in general parameterization, the policies are kind of indexed by some d-dimensional parameter theta, and d is typically taken to be much less than the size of the state and action space. So even if your state and action space sizes are very large, then the number of parameters that you are using to represent the policy class, that is not very large. So this can become useful if the state space is large or infinite. So the advantage of this type of formulation is that this pi theta policies that can be realized by neural network which has the theta as its weights. So so this neural network takes the state as an input and it generates a probability distribution over the action space. And it can be also shown that this kind of formulation of general parameterization that subsumes the tabular policy that I just discussed and the linear CMDP formulation that I just discussed at the special cases. So for example, if I talk about the general direct parameterization, where each of the policy values pi theta AS is assigned a parameter theta SA, and theta SA are taken to be positive, and they are taken in such a way that if you take a summation over A, then the summation exactly becomes 1. So this kind of direct parameterization actually recovers the tabular case, and so we can see that the general parameterization is the generalized version of this tabular and the linear CMDP setups that we just discussed. Now, in this general parameterization, now our original constant optimization problem that changes a little bit. So if you denote the average value function jg pi theta as jg theta, then the optimization problem, constant optimization problem, can now written be as follows. So here we are maximizing the gr theta function, and we are varying the theta over all d-dimensional real parameters. And we are also ensuring that the average value function corresponding to the cost function, jc theta, that is also satisfying the given constraint. Now, what is the problem associated with this kind of optimization, at least theoretically, is that, so since the parameters class pi theta, where theta is varying among all d-dimensional real numbers, so in this cases, the parameters class may not complete all stochastic policies. So in such sense, if you take, you are kind of doing a compression on the policy space, right? So earlier the policies were written as a tabular in the tabular format, or the table size was S cos A. Now you are saying that you are representing the whole class by a parameter theta, where the size of the theta is D. So your D is much less than S cross A. So you are kind of doing a compression. So you cannot possibly represent all the stochastic policies that you are representing before. So due to this kind of incompleteness, the strong duality does not hold in general parameterization. And the effect of this incompleteness is characterized by a certain kind of loss. And this loss is denoted by this term epsilon bias. Now, this precise definition is given in the paper, but here I'm not going through that definition, but this is the intuition behind the term of epsilon bias. Now, so we have already talked about like the general parameterization being the generalization of the tabular cases and the linear CMDP cases. And you can, of course, you can understand that in the tabular case, we have a complete policy because it contains all of the stochastic policies that you can probably imagine. So in those cases, epsilon bias values transfer to be 0. So for direct parameterization or softmax parameterization, which are complete policy classes, we have 0 epsilon bias. But in general, if you talk about any general arbitrary policy class, then epsilon bias, that becomes a non-zero quantity. However, if the policies are represented by policy class is rich, I mean, if the policies are represented by a neural network which has a large number of parameters and which is wide enough and which is deep enough, then the epsilon bias that might become negligibly small. So although this policy class does not contain all the policies, but it contains sufficiently many of them so that the loss becomes insignificant. So, but unfortunately, theoretically, whenever epsilon bias that becomes 0, you cannot show that you'll be achieving epsilon optimality, like the way we showed, like the way some papers showed for the tabular cases. So in these cases, what literature or the existing literature shows that you can achieve the optimality of the form square root of epsilon bias plus epsilon. So you can reduce the epsilon as much as you want, but you cannot control the epsilon bias part. And you can achieve the optimality gap and the constant valuation in both of these format. And the literatures have come up with different kind of algorithms that achieves different type of sample complexities for this type of formulation. So this, the table kind of summarizes what is available in the literature. So here you can see that we have very few papers that concerns the general parameterization in the CMDP setup, and most of them have a sample complexity which is considerably larger than the lower bound that is achievable. So the paper 9, so that says that the lower bound that must be at least 1 over epsilon square, and that is also a factor of gamma. So it also must increase as a factor of 1 over 1 minus gamma to the power 5. But from this literature, you can see that the best that you can achieve is the complexity 1 over 1 minus gamma to the power 8 and 1 over epsilon to the power 4. So there is a considerable gap between what is achievable by the current algorithms and what is possible and what the lower bound says. So the question, the research gap then becomes, is it possible to come up with any algorithm that solves the CMDP problems with general parameterization, and this closes the gap between what is achievable and what is given by the lower bound, and that will be the subject of our current talk. Now, how do I solve this this constant optimization problem for the general parameterization? So although we know that we don't achieve the strong duality, but we can see that this gap between the strong duality and the primal, the duality gap, that can be characterized as a function of square root of epsilon. So with that hope, what we try to do is that we try to solve by this Primal-dual approach. So if you look, if you formulate the dual problem corresponding to the constraint optimization problem for the Jain parameterization, so here it can be written by this first expression that I've written in the slide. So here this function j r plus lambda c theta, so that is exactly the Lagrange function corresponding to that primal problem that I defined earlier. So here first I'll be maximizing with respect to the primal value theta, and then after I'll be minimizing with respect to the dual variable lambda. Now the way this primal-dual approach works is that, so it will try to update the theta parameter and the lambda parameter, or the primal or dual parameter simultaneously. So it will be first fixing the value of theta, it will be fixing the value of lambda, and it will be updating theta along the direction of the theta gradient, and again it will be fixing theta and it will be updating lambda in the direction of the lambda gradient. So however, we do not simply follow the gradient update. We do not simply follow the gradient descent or gradient ascent type of approach. So for the theta, we update it along the direction of what we call a natural policy gradient instead of the actual gradient, that is the gradient of the Lagrange function. And for the lambda, we do kind of a projected gradient descent. So we compute the gradient with respect to lambda by fixing theta, and then we do a projection on a set that is carefully chosen, this lambda set. So lambda set, it is a kind of a set between 0 to lambda max, and the lambda max is a certain parameter whose value will be set according, whose values will be specified later. And here, this eta and the zeta, these are the learning parameters corresponding to the theta update and corresponding to the lambda update. And so here, I would like to focus on the natural policy gradient part. So you can see that this gradient of this Lagrange parameter or the Lagrange function, that is pre-multiplied by the inverse of certain other function or certain other matrix f theta. And this f theta is a certain, it is typically known as the Fisher matrix. So if you look at the definition of the Fisher matrix at the end of this, at the bottom of this slide, then you can see that it is kind of an expectation of the outer product of the score functions. So the score function, the gradient of the lambda log of pi theta. So this function is called the score function, gradient of log of pi theta. And this symbol, this cross symbol, that basically denotes the outer product. So essentially, it means that it is of the form, if A is a vector of dimension D, then A cross A, that becomes A transpose. So that is the meaning of outer product here. And so you compute the Fisher matrix by first computing the outer product and then taking an expectation with respect to the state action occupancy measure that we defined earlier. So nu pi theta is the occupancy measure corresponding to policy pi theta. So the question is, why do we multiply it with the precoder matrix, inverse of the precoding matrix, f theta, and why do we, instead of following the simple gradient update, why do we follow the natural policy gradient? So if you look at the definition of this f theta, then you can see that whenever the theta, pi theta parameter or the policy function changes very rapidly as a function of theta, then f theta value that kind of becomes very large. So if you multiply it by inverse of the f theta, so this kind of minimizes the overshooting that can be caused due to the rapid fluctuation of pi theta. And on the other hand, if the pi theta is changing very slowly, then the inverse of the f theta, that will be the f theta will be very small. So the inverse of the f theta, that will be very large. So in this case, it will also prevent the slow update of the theta. So it is kind of modulating the parameter eta or the learning rate according to how the policy pi is changing as a function of theta. So this is the intuition, and so how do you then compute this natural policy gradient, and how do you solve this entire problem? So before computing the natural policy gradient, so we'd like to state one important result that has been is known in the literature for last more than 25 years now. So this is called policy gradient theorem, and it was published in one of the seminal papers in 1989, this paper 8. And it essentially says that if you want to compute the gradient of this Lagrange parameter gr plus lambda c theta, then it can be computed in the following way. So first you have to do a product between the advantage function and the score function. So we have already discussed the score function between that is the gradient of the log of pi theta. And the advantage function is defined as the difference between the Q function and the V function. So first you have to compute a product between the advantage function and the score function, and then you have to take an expectation of this product with respect to where the S and A are taken from. And the expectation is over the state action policy measure nu pi theta. So this term, this expectation of the product of advantage and the score function, that is defined to be the function h pi theta, and this is a very important function that will keep on coming in our later discussion as well. So it is very important that you keep a note of this function. Now, once we have this result of policy gradient theorem, now we can now compute the NPG, or the natural policy gradient. So by the way, the natural policy gradient computed at theta and lambda, that is denoted by the symbol omega star theta and lambda. Now we can show that using this policy gradient theorem, this omega star lambda theta, that can be computed as a minimizer of a quadratic optimization problem. So this L function that I have written here, so that you can see, it is essentially a quadratic function of omega, and this omega star theta lambda, that is defined as the minimizer of this function. Now this is obviously a convex optimization problem, but with certain assumption we can show that this is a strongly convex optimization as well. And now the strongly convex optimization has several desirable properties that will be that can be exploited. So we can see that we can compute this gradient, we can compute this natural policy gradient by using some kind of a gradient descent method, because omega star theta lambda, that can be written as a minimizer of a quadratic optimization. So we can apply some kind of a gradient descent by iterative process. Now, in order to do that, first let's compute the gradient of this L function. So if you do that, then you can see that the gradient of this L function with respect to omega, that can be written as some linear function of omega. So the first term is f theta multiplied by omega, where f theta is, as you've already discussed, is the Fisher matrix. And the second term is h theta lambda multiplied with some constant 1 over 1 minus omega. Now h theta lambda, so we have already discussed this this function just now. So it is the product expectation of the product of advantage and the score function. And the first term is the Fisher matrix, and it is multiplied with the omega. So this is kind of a linear function of omega that you can see. However, since we do not have exact knowledge about the state transition function p, you can see that we do not exactly compute the this state action occupancy measure nu pi theta, and we also cannot compute the advantage function exactly. So we if we do not have knowledge about the state transition function p, we cannot compute the f theta function, and we also cannot compute the h theta lambda function exactly. So this gradient that you have computed here, that you cannot obtain exactly, then what can you do in that cases? So before discussing that, I would like to summarize what we have discussed till now. So essentially what we are trying to do is that we are trying to form a kind of a listed algorithm. So in the there will be two kind of loop. In the upper loop or in the outer loop, we will be trying to update the theta parameter and the lambda parameter simultaneously. And the theta parameter is updated by following the natural policy gradient, and the natural policy gradient computed at theta k and lambda k, that is denoted by the symbol omega k star. And we are updating the lambda k parameter by following projected gradient descent type of approach. Now, and how do we compute this omega k star, the natural policy gradient? This can be computed by inner loop. So for each of this k, we will be running a inner loop of length h, and where we will be using the gradient of this L function that we just written down, that is the quadratic function. And we will be computing the gradient of that quadratic function with respect to omega, and using that, we will try to come up with an approximate solution of the, or approximate value of the exact natural policy gradient. However, as you have already discussed, that without the exact knowledge of P, which is the typical case for the RL scenario, we cannot compute the JC theta function. So we cannot obtain, or we cannot actually perform the updation of the dual parameter lambda k. And we also do not have knowledge about the advantage function. We do not have knowledge about the state occupancy measure, state action occupancy measure. So we cannot compute the gradient of the L function exactly as well. So so if we do not have those knowledges, then we cannot run the inner loop. So therefore we cannot update the theta parameter as well. So without knowledge of P, we cannot do any of these parameters, any of this updates exactly. So what we can do is that we can go for a sample-based approach. Now, I'm in this talk, I'm not going into the details about the sample-based approach, because this is kind of a standard in the RL literature. But the essential idea is that it will give you some kind of an estimate of the JC function that is used for the dual update, and it will also give you some kind of an estimate of the L function with respect to the parameter omega. Now we can use this kind of estimate, and we can kind of perform an approximate update of the dual and the primal variables. So this sampling process that generates this estimates, it can be shown that these estimates are conditionally unbiased. So if you fix the parameter theta, then the estimate of JC that can be shown to be an unbiased estimate. And similarly, if you fix the parameter omega, theta, and lambda, then it can be shown that the gradient that you are getting for the L function, so that stochastic gradient is also kind of unbiased. So these two are very important results that will be used in our later discussion. So with this, what we are trying to do is that we will be updating the theta and the lambda parameter in an approximate way. So theta will be updated following the direction of an approximate NPG. So the approximate NPG is denoted by the term omega k. So actual NPG is denoted by the term omega k star. And similarly, the dual variable lambda k, that will be updated following the approximate update, an approximate value of JC, which is denoted by JC theta k. How do I, so dual update, this kind of currently understood, but it is not entirely understood that how this omega k will be computed. So for that, we have to run, again, as we have said earlier, we have to run an inner loop, and within that inner loop, we will be computing that omega k. So this inner loop for each of the k will be running this inner loop h number of times, and at each of the steps we will be using the stochastic gradient estimate obtained by the sampling procedures, and this estimate is given by this nabla hat, right? And so in order to so we run this inner loop following a procedure called accelerated stochastic gradient descent procedure, which is described in the paper 5. So here, instead of just updating the parameter omega, just following the direction of the current gradient, what we do is that we kind of update it by using some kind of a momentum. So it is not only updating the omega by just by looking at what is the current value of the gradient estimate, but it is also looking at what was the estimate in the earlier instances. So I'm not going to the details about this convoluted step, but this is given to show that this process is kind of convoluted. So, so this is the kind of summary of the algorithm that we have developed. So the question is how well this kind of algorithm performs, and what is the sample complexity that you can get. So we, in order to analyze the performance of this algorithm, we have to assume a bunch of assumptions. So we are not mentioning these assumptions here, but these assumptions are kind of standard, and they are used by all the papers in the policy gradient literature. So using this assumption, we can show that the gradient of the Lagrange function jr plus pi c, jr plus lambda c theta, this Lagrange gradient, that can be bounded by some constant which grows as 1 over 1 minus gamma square. And also you come up across a very important result. So that essentially says that how the global convergence of the Lagrange value or Lagrange functions, that is connected to the local convergence of the NPG values. So if you look at the second inequality, you can see in the left hand side, we have the difference between the optimal value of the Lagrange function and the Lagrange functions computed at theta k and lambda k. So this is kind of an optimality gap that you encounter at the kth step of the outer loop, and you are kind of taking an average over all this average optimality. You are kind of computing an average optimality gap. And in the right hand side, here several terms. So you can see that the first term is involved with at the difference between the conditional expected value of the omega k, which is the estimate of the NPG, and the actual value of the NPG, which is omega k star. So this difference between the expected value of omega k and the omega k star, that can be interpreted as the NPG bias with conditional NPG bias. And the second term is square root of epsilon bias. So this is also again coming from the incompleteness of the policy class, and we cannot do anything about it. This term will be present due to the incompleteness. And the third term, here you can see that we have some kind of a second order term. So it is kind of the expectation of the norm square of the approximate NPG that you have computed. And there is a fourth term. So this is kind of a constant term which goes as 1 over eta k. Now you can see that if we can bound the second order term by a constant, then the second order and the last term, they will both form a bound of the order of eta plus 1 over eta k. So if you just substitute eta equals to 1 over square root of k, then these two terms together that can be bounded as 1 over square root of k. So that is that thing that we'll try to do in the next slide. So here you can see that this second order term that we just talked about, so the expectation of the norm square of the NPG estimate, so that can be bounded again, it can be decomposed into two terms. If you look at the second term, then it can see that this is the essentially the gradient of the Lagrange function. And we have just talked about, we have stated one result where you show that this gradient of the Lagrange function that can be bounded by a certain constant number. And now the question therefore becomes, how do we bound, or whether it is possible to bound the first term, so which is kind of the difference between the NPG estimate omega k and the actual omega NPG value omega k star. So for the second term, we get a difference between the omega estimate and the omega actual omega value. And from this NPG bias, we get a difference between the expected value of omega k and the actual omega value. Now, how the question therefore becomes whether it is possible to bound, and if we can bound, then what is the upper bound, and so on. So for that, we have to perform an analysis of the AISTATS method that we just described, which is used in the inner loop. And so I'm not going into the details of the analysis, but the summary of this analysis is that the difference between the NPG estimate omega k and the actual NPG value omega k star, this expectation can be bounded by a sum of two terms. If you look at the first term, so this is sigma square by h, and the second term is exponential minus h. So this sigma square, this can be considered, this is a constant in our analysis. And this sigma square can be considered or interpreted as the scale noise variance of the gradient estimate of the L function that we are using in the inner loop. So if we, so this is essentially arising because we do not have access to the exact gradient of the L function. If we had that, then this sigma square value would be essentially equal to 0. But since we do not have, then we cannot put that to be 0. So you can see that this expectation, expected difference between the omega k and omega k star square, so that can be bounded by this term, which can be further bounded by some constant, because 1 over h is bounded by constant, and exponential minus is also bounded by constant. And this bound is sufficient for our analysis. Now, once we bound this term, the next question becomes, how do we bound the NPG bias term, the expected, the difference between the expectation of omega k and the actual value of omega k star. Now, if we try to bound this term by just following the result that we have stated for the, the result that you have stated in the top of the slide, then we can just apply the Cauchy-Schwarz type of inequality and come across, and we can derive this type of bound. So this bound also has two terms. The first term is of the order of 1 over square root of h, and the second term is of the order of exponential minus h. However, this is a very naive bound, and we'll be showing that by looking at certain properties of this AISTATS program, we can actually drastically improve this bound, and this is important to establish the result that I'm going to show at the end of this presentation. Now, so to understand that, how do I improve the result for the NPG bias? So let's again look at the AISTATS process that is used in the inner loop in order to compute the approximate value of the NPG. So this is again, we are kind of reiterating the process that I've stated earlier. So I would like to emphasize here 2 points. So you can see that if you look at the steps of this AISTATS process, then you can see that some of the steps are essentially kind of a linear combination type of step, and some of the steps are kind of using the gradient estimate value, which is given by which is denoted by the term GH hat, right? Now, let's try to look at one of the important properties of this GH hat, this kind of estimate. So you can see that if you compute an expectation of this gradient estimate GH hat, condition on the value of theta k lambda k, then it can be easily shown that this exactly equals to the exact gradient value of the L function computed at omega, which is the expected value of yk given theta k lambda k, right? So you are kind of showing that if you take an expectation, conditional expectation on GH, then the expectation actually removes the so that expectation can actually be taken inside the first argument of this L function. So this is an important result that we have to focus, and this will be used later on for our further analysis and proving the result. Now, the second observation is that, so if we apply this conditional expectation on given theta k lambda k on each of the steps of this ASCT, then what do we get? So we get a very similar type of update, but here you can see that instead of using a GH hat, we are using an actual gradient value of the L function. We are not using any kind of estimate. We are using actual gradient value, right? And here you can see that so you can see that this update is with respect to y bar, and each of the y bar is kind of the conditional expectation of this different terms with and the condition is on for a given theta k and lambda. Now from this observation we can actually so if you look at this update, you can see that this resembles an update ASCT update process when the gradient is exactly known to you, right? So this is so this resembles an update process as if you have access to the original gradient, not the expected or not the estimate of the gradient, right? So if we have to essentially compute the expectation of omega k given theta k and lambda k, and you have to compute the difference between this term and the actual gradient, then we don't need to go through our naive the bound of the NPG bias. Essentially, what you can do is that since the computation of this expected value of omega k given theta k and lambda k that looks like an ASGT update that uses the actual value of the gradient, not its estimate, we can substitute sigma equals to 0, and then we can bound the expectation of the NPG bias by this exponential of -e this standard term. So if you look at the naive result of this NPG, then earlier we had sigma by square root of h this term. But due to this observation, now we can remove the sigma by 3 squared a squared square root of h term, and we can only get this kind of bound, which is exponential of -h. Now, if you substitute everything, then you can in the local to global result that we stated earlier, then you can show that the optimality gap of the Lagrange function that is bounded by essentially three terms. The first term is essentially the square root of epsilon base that is coming due to the incompleteness of the policy class. The second term is exponential of -e that is coming due to the bound of the NPG bias, and the last two terms that is coming due to the bound of the second order term and the 1 over eta k term that we had earlier. Now, this is the kind of result, or this is kind of a global bound for the Lagrange function. What we essentially want to do is that we want to prove the optimality gap for the reward value function and also for the cost value function, right? So we are not again going through the details of this process, but what we have proven that if we try to extract this kind of optimality gap for the reward function and the cost function from the from the optimality gap of the Lagrange function, then for the reward optimality gap, you will encounter an additional term of order of an additional term which is a order of zeta. So when you will be writing the optimality gap with respect to the reward value function, then you will get all these three terms plus some additional term which is of order of zeta. So in similar manner, if you want to bound the constraint violation, then you will get all these three terms plus some additional term which is of the order of zeta plus 1 over zeta k. Now, if you substitute this eta as 1 over square root of k, and if you substitute zeta as 1 over square root of k, then you can show that the optimality gap of the reward value function that can be bounded as square root of epsilon base plus exponential -h plus 1 over square root of k, and similar result we can get for the constant violation. So if we choose k as a some order of epsilon square and h as the order of log of 1 over epsilon, then you can show that you can achieve an optimality gap of epsilon base plus epsilon, and you can also achieve a constant violation of the form of square root of epsilon base plus epsilon with a sample complexity that goes as 1 over epsilon square. So this is the final result that we would like to state in a very nice way. So in our earlier discussion, we did not account for the term 1 over 1 minus gamma, but if we do the detailed calculation, then the sample complexity that turns out to be 1 over 1 minus gamma to the power 7 and 1 over epsilon square. Now I would like to remind you that the state of that result that is available for the general parameterized CMDP, that gives a sample complexity of 1 over 1 minus gamma to the power 8 and epsilon 4. So we are not only improving the power of epsilon 1 over epsilon, but we are also improving the power of 1 over 1 minus gamma. And by the way, the power of epsilon that we are getting here, that is exactly matching with the optimal the lower bound that is provided in the literature. So the optimal lower bound or the lower bound available in the literature for CMDP is 1 over epsilon squared. So at least we are touching the lower bound in terms of epsilon, even if it is not with respect to the power of 1 over 1 minus gamma. So finally, I would like to conclude that so although this result does not prove a zero constant violation, which is a desirable quantity, uh, so this is not a very hard thing to do. So there is a special trick called conservative constant trick. So this has been applied in many papers. So if we apply this trick, then we can also show that how we can also come up with an algorithm that also achieves zero constant violation, which will be very similar to the analysis that is given here. And finally, I would like to mention that why the importance of the observation that I mentioned earlier, that the expected bias can be, this written as not as 1 over square root of h, but as a, exponential minus h. So without this improvement in the upper bound of the bias, and without observing that this bias can be written as an error corresponding to an ASCT program with the exact value of the gradient, not its not its estimate. So the sample complexity will be in the order of 1 over epsilon 4, not in the order of epsilon square. So this is a very crucial observation and a very important result that is used to decrease the sample complexity of the result. So what are the extensions and future work? So this work essentially considers the optimality gap and the constant violation in the average sense. So if you look at the result here, then you can see that the optimality gap is computed over all parameters theta k, where k varies from 0 to k minus 1. And similarly, the constant violation is also in the sense of average, is computed in the average sense, because you are computing the constant violation for each theta k, and then you are taking an average over all k, and you are kind of bounding that. But ideally, what you would like to get is that you would like to get a last iterative result. So you would like to show that the last iterative that you are getting, that means the theta k that you are getting at the last k, so that satisfies some optimality bound, and that the corresponding the constant violation that is also bounded. So we would like to get results in that format. So we have recently just published another paper a few weeks ago. So in that paper, we are kind of shedding a result on that, but the result that you are getting, that is not optimal. I mean, there is still some gap between the result that you are getting and the optimal lower bound. And a second question that we can explore is that although we have achieved optimality in terms of epsilon, so there is a still gap between the upper bound and the lower bound in terms of 1 over 1 minus gamma. So can we come up with an algorithm that improves the power of 1 over minus gamma? And also the final question is it possible to come up with an algorithm that can use this kind of observation, the clever observation that we have observed in this case, to extend or come up with a better algorithm for other type of RL problem. For example, the inverse reinforcement learning problem, or reinforcement learning with a fairness, which can be formulated as nonlinear CMDP problems. So with that, I would like to conclude, and thank you for listening. So if you have any questions, I'm happy to answer that.
Thanks a lot, Professor, for an informative talk. I request the audience to feel free to ask questions if there are any. You can also type them in the chat box so that I can relay. I think there are no more questions, Professor.
Okay. Thank you.
But thanks a lot for accepting our request and giving the talk within a short notice. And thank you everyone for joining the today evening. And yeah, thank you all for attending.
Okay. Okay. Bye.
Thanks a lot, Professor. Bye.